السلام عليكم ورحمة الله وبركاته. شلونكم؟ عساكم طيبين. Today we have a really special guest that's going to be discussing some really interesting things that many of you will find very fascinating. We are honored today to have Dr. Charles Lashy, who is a professor of electrical engineering and planetary science at Caltech. He was previously the director of JPL for 16 years. And in those 16 years did a lot of amazing things. Dr. Lashy is originally from Lebanon and left Lebanon to study in France, as well as the US in Caltech. And he is also working on several initiatives at CAXT in Saudi Arabia. So I don't want to take up too much of your time. With that, I give the floor to Dr. Lashy. Thank you so much for being with us.
Thank you, Michelle, and good evening, everybody in the kingdom and across the Middle East or across the world that they are watching. So if we can put the first slide, on. Yeah, so first I want to start by thanking the Saudi Space Commission for inviting me on giving this talk. As you can see, I'm also very closely involved with CAXT in the kingdom, who are doing a number of joint projects, with them. So what I'm going to talk about today is what's happening in space exploration and the excitement of what is happening, as well as to tell you about the future, what we're planning to do. So if we go on the next slide, like every young kid, if we go on the next slide, please. So it's like every young person, if you go out during the night and look at the sky, it's amazing what you would see. You would see all these stars and these galaxies. This is a picture taken with the Hubble telescope, and it covers a very, very small part, of the sky. And look how many stars and galaxies exist in our beautiful sky. If we go on the next slide, so if you zoom on one of these galaxies, it will show you how literally it's made of billions of stars. So again, if you go to the next slide, please. So, and if you look around some of these stars, if you zoom on them, you actually see the planets. So this is like our solar system. These are the كواكب that are حول الشمس تبعنا, and you can see completely to the left, that's Mercury, then you have Venus, then you have Earth, it's that little blue dot, and then you go to Mars, Jupiter, Saturn, Neptune, and Uranus on it. And we're finding that almost every star in the sky actually has planets around them, not necessarily similar to ours, but a little bit different. So what I'm going to do today is to tell you a little bit about the exploration that we have done for some of these planets. So if we go on the next slide. So the one that we have been focusing a lot on is the planet, the planet Mars. And the reason we focus on Mars, in Arabic, that's Marikh. The reason we focus on Mars, it has a lot of similarity with Earth. On the left, you see Earth, on the right is Mars. You can see there are polar caps on Mars. You see that at the bottom, which are made of ice, water ice. And if you go on the next slide, you see that the geology on Mars is very similar to the geology on Earth. So in the next slide, you can see on the left, that's a picture of the Grand Canyon in Arizona on Earth. On the right is a picture of a Grand Canyon, on Mars. And here, if you look at the surface, taken on the right is the Earth. It looks very similar to many desert places like Saudi Arabia. On the left is Mars, which was taken with a rover. So the point I want to make is that the geology on both planets, Mars and Earth, are very similar. Mars has an atmosphere, but much thinner than our atmosphere. So you cannot go out, if you are an astronaut, you still have to put a spacesuit on because it's very, very thin air. So it would be like if you were at about 30,000 meter altitude. So that's about how little air there is on Mars, but there is some air on it. And the geology is very similar. And we believe early in the days on Mars, actually there was water on the surface, similar to Earth. But as things have evolved, the water kind of evaporated or frozen below the surface. So a key question that we're trying to find is, could have life evolved on Mars like it evolved on Earth? And if it evolves, how far it evolved and where can we find it if it still exists, on that planet? So if we go on the next slide. So one thing people don't appreciate that literally for the last 17 years, we have had Rover on Mars all the time, continuously. We had a series of missions. And you see on the left is a picture of these rovers, in our test sites at JPL. We started with a little teeny one that you see, which is called Perseverance. It's about the size of a shoebox. Then we went to Spirit and Opportunity, that's the one which is about the size of your desk. And then we have, after that, we had Curiosity and Perseverance, which are the size of a car. And the one on the right, that's a picture of the last rover taken on Mars itself. The rover has an arm and there is a camera at the end of the arm, which actually took a selfie, if you want, of the rover. So you could imagine that continuously humanity, all of us, through all our international effort, we had continuous presence and continuous exploration of the planet Mars. So if we go on the next slide. So I wanted to give you an idea about the challenge that it is to send a spacecraft to Mars. It takes typically about 6 months to 9 months to get to Mars with our present technology. And after we travel about 225 million kilometers to get to Mars, we have to arrive within a 2-kilometer circle to make sure we are at the right angle and landing at the right location. And to give you an idea, what does that mean? If we go on the next slide. So that's kind of the equivalent that if I go outside here and hit a golf ball from California towards the kingdom, the golf ball has to go straight in the cup. That's how accurate we have to do the trajectory. And to make it a little bit more challenging, Mars is moving. So it's like your golf cup is actually moving and you still have to get it straight in the cup. So we had to develop a lot of technologies to actually basically be able to navigate and arrive at that right angle on the Mars planet. If we go to the next slide, the other challenge is when we arrive to Mars, we're coming at extremely high speed. And the energy that is in the spacecraft, at that speed is kind of the equivalent of 18,000 race cars going at full speed. And then we have about 5 minutes to slow down and land on the surface very softly, so we don't damage the spacecraft. So this is a big challenge, and basically what we do, we use heat shield, then we use parachutes, we use retro rockets, and I'm going to be showing you shortly a video about how we actually do the landing. So if we go on the next slide. So this shows you a picture of the latest rover. That's in the assembly room at JPL. As I told you, it's about the size of a car. It has 6 wheels. They are all run electrically. The power source is a small nuclear generator that we call RTG. It's basically use the decay of plutonium to generate heat, and then from the heat we generate electricity. This rover runs on only about 150 watts. So that's about one bulb, light bulb in your room. So we had to develop a lot of advanced electronics which can operate at very low power and operate for long period of time. The rover has a dozen cameras. You can see one big camera at the top, which looks like pink. That's a laser system with a camera. And this rover has all the scientific equipment that you find in a chemistry lab at a university. So it has an oven that we can put sample in the oven and heat them to see what material evaporate from, what gases evaporate from that material. We have an X-ray machine, we have a gamma ray machine, a spectrometer, effectively all what you would find in a chemistry lab at the university to analyze the composition of the rocks, or what you would find at a lab at Aramco, which used to look at finding the different rocks in the kingdom and what they are made of. So all of that, we have to compact it, in that rover. So if we go on the next slide. So to give you an idea, how do we package this to put it on top of the rocket? So you can see at the bottom what we say rover. So the rover is folded in. So the wheels are folded under the chassis. Then we put it under what we call the descent stage. So that's a stage which is going to be bringing it down to the surface, and you can see the retro rocket on it. Then we encapsulate all of this with a heat shield in the front and a back shell, in the back. And then all of these are carried by a cruise stage. So the cruise stage takes us all the way to Mars and then drop the package inside the atmosphere, on Mars. And then after a parachute opens, supersonic parachute, it's the biggest parachute ever built. And the heat shield, so between the heat shield and the parachute, that slows us down, about 90% of the speed. Then as we get close to the surface, the retro rocket, we drop the heat shield, we drop the back shell, the retro rocket, basically fire, so it slows us down, so we can come to the surface relatively slow. And about 20 meters above the surface, we use a sky crane, like a long rope to bring the rover slowly down to the surface, so it touches the surface very slowly. And in a minute, I'll be showing you a video about how did that all happen, because we had cameras everywhere. We had cameras looking up, we had cameras looking down. So it will be like if you are sitting on the rover and you'll see in real time how we're landing on the planet. So if we go on the next slide. So this is where we were assembling the rover. This is what we call the high bay. So you can see as they are marked, you see the rover where it says Mars 2020 rover. You see the descent stage next to it and the cruise stage next to it. So that's a place where we build all our spacecraft. And if you can see the people there, they are all dressed in what we call bunny suits or white suits, because we want to make sure everything stays very, very clean. We go on the next slide. So now I'm going to take you to the mission operation room. So this is the mission operation room where we control all our spacecraft. As of now, we have almost 20 spacecraft across the solar system, be it on Mars or Venus or Jupiter or Saturn. And that's where we actually are monitoring almost in real time, all these spacecraft that they are flying. So now I'm going to go, if we go to the next one, which is a video. So this is a video which show you actually what was happening when we landed, Curiosity. So
we're starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Now you see the parachute open.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
And
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the
So
surface.
that's the heat shield with dropped, and we see Mars in the background. So this is all real images which were received as we were doing the landing. And as you can see, Mars looked like a very dry desert area, but what you see, what looks like old rivers.
Filter converged. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface.
And the reason you see it moving back and forth is because we wanted to land in a very specific
Continuing
area.
to descend on the parachute. We're coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engine.
And you can see the sand dunes, on the surface of Mars, similar to what you see in the Kingdom.
Shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about...
Oops, it looks like it skipped the last part. Wait, can you go back on the video? Did you skip the last part? So anyway, so basically,
We are starting to straighten up and fly.
yeah, let's leave it. Maybe I can see it again because there was a interesting part at the end. Okay, that's fine. So anyway, so you kind of gave you an idea, of the landing and the challenge of the landing that we had on Mars. So the first thing we do after we land is to actually take pictures. It's a camera just below the rover to make sure that everything is working well. So that was the first picture we took, with the rover. If we go to the next slide, and you see the shadow of the wheel here. So if we go to the next slide, so the first thing we do is to start test the different subsystems, on the rover. So now you see the wheel, one of the wheel, we were checking it. And then this is a robotic arm, we were checking the robotic arm that everything is working well. Then if we go on the next chart, and the robotic arm is very similar to your own arm. It has, elbow, and so it actually we can manipulate it to collect samples. And what the rover will be doing over the next, so this rover landed literally, let me think, today is the 19th, so about exactly a year ago. And then what we are going to do during that period and in the future is to actually take samples from the surface, like you see to the left. The sample is about the size of your finger. Put them inside a sample tube, seal them, and collect about 31 samples, put them in a container. And then put that container in a location on Mars. And if we go to the next slide, because what we want to do is in the future, we want to send a mission to the surface of Mars to bring those samples back. So you can see on the left is Perseverance, which is the present rover, which is on Mars. It will be roving over an area of about like 50 to 100 kilometers, looking at interesting samples, similar to what a geologist will do, when they go to the field and they're doing exploration. Then in 2028, we're planning to send another lander, which will bring that capsule of samples, put them in the nose of a rocket, and launch it in orbit around Mars. Then we'll be sending a spacecraft to go rendezvous with those samples, bring them back to Earth so we can analyze them in laboratories here on Earth. And this is going to be done as an international mission. There would be involvement from the European Space Agency, the British Space Agency, and many space agencies. So really it's a humanity kind of activity to collect samples and then bring them back to Earth. So if we go on the next slide. Yeah, if we go to the next slide, please. Now, one thing which was interesting on this mission, we also added for the first time a small helicopter on it. Now, the challenge of this helicopter, even that, you know, the technology, we have it here on Earth, is, as I mentioned to you earlier, Mars has an atmosphere which is only 1% of the atmosphere on Earth. So it's about the pressure of, if you are at 30,000 meters, much higher than Mount Everest. So flying a helicopter with such a thin atmosphere has been a big challenge. If we go to the next slide. So that shows you the actual helicopter and the people assembling it. So we had to develop a very, very, very light helicopter. It weighed about 1 kilogram. And that includes all the electronics, the structures, the cameras, everything. And the helicopter has to be autonomous because it takes about 20 minutes for the signal to come from Mars to Earth and then from Earth back to Mars. So you cannot joystick it like you do with a helicopter that you are flying or the toy you are flying. So it has to have all the intelligence of actually not only flying, but deciding where to actually land and to avoid rocks, you know, so it doesn't tip. So if we go on the next slide, which is a video, that will show you the flight that we have done on the surface. And imagine this is the first time ever that we have flown a plane or helicopter on another planet. So this is like 100 years ago when the Wright brothers, you know, flew here on Earth. This is the first time we fly on another planet, and you see the helicopter, you know, kind of moving across the scene. And now, originally we started it as a technology experiment, but now it's being used to actually survey ahead of the rover. So it can go like over the next hill, take pictures, send it to the rover. So we can decide where to send the rover. So it's basically like a scout when you are on an expedition and you send a scout ahead of you, you know, to actually go and survey the area and decide where to go. And here you see it coming back and landing. And of course, we were very nervous when we did the landing because you want to make sure you don't land on a rock and then tip the helicopter. So if we go on the next slide. Yeah, I guess we can go to the next one. Now, let me tell you a little bit about some of the other activity, even that Mars gets the most attention. But let me tell you about some of the other activities that we're doing. So this is a mission which is around Jupiter. So I Googled to see in Arabic, it's Mushtari. And this is the biggest planet in the solar system. And this spacecraft has been orbiting it for the last 6 years. If we go on the next slide. And the reason we are interested in Jupiter is to see the dynamic of the atmosphere, you know, of Jupiter. Like you see this picture, this is a close picture, and all of these features look like they are like hurricane, like that white circle in the top or to the right, it's bigger than Earth. And you can see all these hurricane and the dynamic of the atmosphere, which could give us information about our own atmosphere and about the hurricanes that we have in our own atmosphere. So if we go to the next slide. That's a farther out picture of Jupiter, and you can see what we call the red spot. So that red spot, which has been observed for hundreds of years. So that's like a long-term hurricane, and it's bigger than our planet Earth. And the reason I wanted to show you, these are real color. So if you were on that spacecraft, that's what you will see. But one interesting satellite of Jupiter, you see it on the top left, that's called Europa. So if we go on the next slide. Now, Jupiter has 4 big satellites, but the one which is particularly interesting is Europa. And the reason Europa is interesting, it's made of ice, water ice, but also you see these fracturing and these cracks, and you see this brown material on it. So we believe that Europa, below the surface, there is an ocean below the surface, similar to our ocean. And as we speak, we are building a spacecraft which will be launched to Jupiter, go in orbit and map Europa in more detail and do sounding of the ice to see how thick that ice is. And we believe that in some location, it might be only a few hundred meters, because in the future, we would like to land a spacecraft on the surface, drill our way to the ocean and see what's in that ocean. Could there be life in that ocean? Because the brown material is organic material. So we have water, we have organic material, and we have heat because of the tide, on Europa, which melts the ice to make it water. So the question is, could life has evolved in that ocean similar to how it evolved here on Earth? So this mission is going to be launched 2 years from now, and it will get to Jupiter close to the end of the decade. We go to the next slide. The other planet that we are really very interested in is Zohar, which is Saturn. And Saturn is a beautiful planet because it has the rings around it, but also it kind of represents how the early part of our solar system actually formed. So imagine that Saturn itself, that the sun, is at the center of our solar system. There were dust around it, which formed ring, and that dust accumulated, became bigger rock, and then formed the planet. So Saturn will allow us to study actually how our solar system actually formed. And recently we had a mission called Cassini, which spent about 13 years around Saturn. And it just finished about 2 years ago. And we mapped all the satellites around Saturn like Titan, and we did detailed studies of the ring of Saturn itself. If we go on the next slide. Now, part of our long-term goal, because I'm sure I saw in the chat, some people were talking that they want to be astronaut and travel to that planet. Well, it's very possible in our lifetime that would be able to go back, to go first to the moon, but ultimately to Mars. So our key objective is to develop the capability and the technology to be able to travel to Mars. But in order to do that, as I told you earlier, it takes about 6 to 9 months to get to Mars. So it's going to be a big challenge, both for the travel, to take the food, the water, everything with us. So we're doing that in a stepping stone. And the first step is to go back to the moon and establish bases on the moon, regular bases, not only like what we did in the Apollo program where we went, spent a few days and came back, but to actually go and stay there on the moon, develop technology and testing so we can prepare for going to Mars. And in the United States, NASA has a program called Artemis, which is basically to go back to the moon in the next 4 or 5 years. And it's an international program. It involves lots of nations, Europe, Japan, many nations are involved in the development of that mission, and many nations are developing elements which will allow us to develop those stations on the moon. So it's really an international effort to get back to the moon and then ultimately to get back to Mars. And I'm sure some people are thinking, well, could we go to Mars in our lifetime? I think within the next 20 years, we will have the technology and the capability to actually send the humans, to Mars. We go on the next slide. So that kind of gives you an idea about all our planetary activity, but also very important is to look at our own planet and to see what is happening on our planet, particularly with the concern about global warming and the changes which are happening on our planet. So if we go on the next slide, I'm just going to give you a couple of samples of what we are doing related to our planet and the observation of our planet. So if we go on the next slide. So we have four major focus, at NASA in our program, and in a number of these areas, the kingdom is working with us. We have a joint program between Caltech, JPL, and CAXT in Riyadh. One area is looking at the changes in the ocean, the sea level. Another area is about availability of water, particularly in the Middle East. That's a big challenge to see how and manage the water that is available. To look at what's happening in the atmosphere, the carbon, which actually is leading to increase in temperature, and then to looking at extreme events like earthquake, hurricane, floods, and so on. So I'm going to show you just some examples of what we're doing in that area. If we go on the next slide. And these changes are very driven by the global warming. For instance, one example, we have been monitoring the ocean height for the last 20 years, 30 years. And we are seeing that the ocean is rising little by little. It's few millimeters per year, but after 40 or 50 years, that could get to many meters, and then many areas around the coast will be flooded. So this is of major concern that the ocean rise. And the ocean rise is driven by two factors. If we go on the next slide. One factor is the global warming. So as the water gets warmer, it kind of expands. And the other factor, we have been monitoring the polar ice in Greenland and Antarctica. And as the planet warms because of the carbon dioxide in the atmosphere, the ice is melting. So as you see at the top right, it shows you how many gigatons of ice is melting every year. So it goes up and down depending if it's the summer or the winter, but on the average, it's going down. So all that ice which is melting is going into the ocean, and that's what leads partially to that ocean rise. If we go to the next slide. So it is a major concern about the change in the temperature. So we have a whole activity of monitoring what's happening on our planet. On the left side, it shows you the different instruments that we have been flying, which are monitoring the globe. So we can monitor the temperature, we can monitor the amount of carbon dioxide, we can monitor the wind, we can monitor aerosol in the atmosphere, methane, and we use not only spacecraft, but also we use airplanes and we use drones to be able to continuously monitor what's happening on our planet. If we go on the next slide. So in matter of fact, in 2 years, we're planning to launch a mission, which is called NISAR. That's a mission which is jointly with the Indian Space Agency. And that's what that mission is. It's an imaging radar. So we use radar techniques to image the surface. And basically, we will be able to map the whole planet every 2 weeks, and not only to take images, to a resolution of few meters, but also to measure the changes. Like if there is any change in the surface of literally down to centimeters, we will be able to map it. And I will tell you in a minute why is that important. If we go on the next slide. That's an activity that we're working jointly with CAXT, about. So let me show you an example of what we'll see. This is the Los Angeles basin. And you are seeing the surface changing down to centimeter. You see at the bar, which shows a centimeter, and you can see the surface moving up and down. The reason it's doing that is as we are pumping water from the wells, the surface actually subsides a little bit. And as the snow melts in the mountain and then feeds the subsurface, then it moves up a little bit. So by monitoring the changes in the surface, we can determine exactly how much water is being pumped And is it going to be replaced? So just imagine we'll be doing this for the whole kingdom, in fact, for the whole world, but particularly important for the Middle East and the kingdom. And we'll be able to see how much water is being pumped from below the surface and is it being replaced? And if we are losing the water, then we have to manage it better. Also, if we are pumping oil, you'll actually see the surface subsiding. If there are motion resulting from tectonics or plates like the Red Sea across the western part of the kingdom, there is a major fault in there. And that's why every once in a while there are earthquakes on it. We will be able to monitor it. That's very important for construction. So if you have pipeline, if you have water pipe, if the surface is subsiding or if there is any displacement, we need to know that ahead of time. So to be able to do the construction better. Example, the city of Neom, which is going to be under development in northwestern part of the kingdom. It's important to see the surface, how much is the surface moving because of the Red Sea fault, and therefore to build things, better. We have that issue here in Los Angeles all the time. That's why most of our buildings here are built on rollers. So when an earthquake happens or there is motion on the surface, it can easily move without damaging the building. If we go on the next slide. Now, one of the things that we have developed here is what we call Eyes on Earth. So this is a program that you can Google on Eyes on Earth, and you can see it, and it will give you every day all the satellite data that we are receiving, on the satellite for all the different parameters. So like now you are seeing possibly the carbon dioxide, which is in the atmosphere, or carbon monoxide. So you can get it on your iPhone and be actually able to monitor it. So this will be able to have all the agencies, the government agencies, the public, to actually see what's happening in our atmosphere. And if we go on the next slide. So this is a way of monitoring our planet continuously. I think if we go on the next one, and one of the things that we developed with our colleagues, at CACS, is to have an Arabic version of the system. So now you are seeing it. So if you don't want to look at it in English, you can look at it in Arabic. And CACS played the lead role in developing that capability in Arabic. So if you go and Google Eyes on Earth or Al-Ard Al-An, you can get on that website and have it on your iPhone. So you can show your friends about literally what's happening on our planet literally that day, and it's updated regularly. Also on that application, it will show you where every satellite is. And it will give you, if you click on the satellite, it will give you information about that specific satellite, what is its size, what it's measuring. So this will allow us to monitor our planet on a continuous basis and see what are the changes which are happening on our planet. And I think if we go on the next one, I think this might be the last slide in the presentation. Can you go to the last slide? So again, I want to thank the Saudi Space Commission for inviting me. I want to thank my colleagues at CACS, King Abdulaziz City of Science and Technology, who have been working jointly with us, particularly on this Eyes on Earth. And one of the messages I want to leave you is that jointly with the kingdom and internationally, we are doing what we call dare mighty things. That means here as humanity, we want to push the limit of knowledge and the limit of exploration. So we take these challenges, to actually get better information, not only about the solar system, but also what's happening on our planet. So again, thank you very much for listening to that thing. I hope you enjoyed that presentation. And Michal, I guess I turn it back to you for any questions.
Thank you so much for this very informative session. I think everybody learned a lot from it and from your experience. I do have some questions I would like to address that the audience might benefit from. One of the questions I have is, you've mentioned these missions, this Perseverance rover, and so on. How long does it take to plan such missions?
Yeah, that's a very good question, because these missions require a lot of planning and a lot of technology. So typically for planetary mission, we start thinking about them about 15 years ahead of time. And then it takes the time to design it, convince the government to fund it, NASA and the government to fund it. And then it takes typically about 5 to 6 years to build them, like the rovers on Mars. And then it will take like 9 months in the case of Mars to get to Mars. In the case of Jupiter, it takes 3 years. In the case of Saturn, it takes like 5 years to get there. So typically these missions take anywhere from 12 to 15 years. So you have to be very patient and very dedicated, to stay to work with them. So that's typically how long it takes. Now, Earth orbiting mission take less time. So it takes like about 5, 6 years, to do that. But for planetary, we have some mission which we launched literally about 30 years ago, like Voyager, and it's still working. Matter of fact, 40 years ago.
So when you do plan missions like this or come up with an idea like, hey, we need to address this, we need to learn about something, what is there like a template phase to build on this? Like, you say phase 1 means I have to do these tasks, phase 2, phase 3, and so forth.
Yeah, we do it in phases. I mean, at the beginning, what we call phase A is basically designing in general, what are we going to do, what kind of instrumentation we need, and doing preliminary design and drawing without building anything. Then we start going into the detailed design, of it, and we usually build what we call breadboards. That means we start first building part of the hardware to test them, to make sure they work well. And we always, particularly in the case of planetary, because we are in extreme environment, either it's very cold or it's very hot, it's radiation, it's in vacuum. So we test all these to make sure they work. And then we assemble it all together, and then we test the whole spacecraft. And typically, like in the case of the rover, at the peak, we had almost about 800-900 engineers working on it. Both at JPL as well as in industry, as well as international. So it's really a major team effort to develop these kind of capability.
And so when you have a target planet or a target area that you want to go to, what are things that you need to consider? Like, for example, at what point in terms of a distance away from the sun, do you start considering using nuclear type or like RTGs and so forth in order to decide, like, can I use solar panels in this case? Can I use RTGs for this case? And what is the proper power architecture that I need to use for this sort of mission?
Yeah, clearly we need power to run our spacecraft or our rover. So typically, if we are going closer to the sun, like Venus and Mercury, or somewhat on Mars and a little bit on Jupiter, we can use solar power. That means we have enough sunlight to generate from solar panel. But as we go farther out, then we don't have enough sunlight. So we actually use what we call a nuclear power source. And basically what it is, we use nuclear material like plutonium. And as the material decays, it generates heats. And then we use what we call thermocouple, which takes that heat and generates electricity from it. The advantage of the nuclear is you can have power for literally 60, 70, 80 years. Example, Voyager, which we launched in the middle of 1970, is still working. After 40 years, it's still actually working. The solar power, after a while, it starts decaying, depending on the technology we're using. On Mars, we're always concerned that the dust will accumulate, on the surface, and therefore we lose the power. So power is a key factor. The other one is the thermal property. As we are out in space, it gets very, very cold. So we also have to preserve the heat. Also, like around Jupiter, there is radiation, so we have to protect the electronics, from radiation. So we have to take all of this into account and do simulation, of these things. So these are the factors that we include in our studies.
So as you mentioned, with the radiation around Jupiter being the highest in our solar system, what precautions do you take in planning a mission in order to harden the electronics such that you guarantee that it works? Because if it takes 3 years to get there, you don't want it to get there and be like, oh, we fried all the electronics.
Yeah, no, you are absolutely right. So we do two things. One, we do shielding. So we take the electronic, we put it inside a shielded box, which protect from some of the radiation. The other one, we design electronics to have like redundancy, to make sure that if part of the electronic get damaged by the radiation, there are other parts of it which we can do that. So we have developed a lot of capability of shielding and redundancy in the electronics to protect us from the radiation, particularly in the case of Jupiter, which is the worst one from radiation point of view.
And when you create these missions and when you create your team for a specific mission or whatever objective that you have, whether it's planetary or something orbiting a planet, what kind of people do you hire? I wanted to shed light on this because I wanted the audience to understand that this is an intensely interdisciplinary type mission design, and it's not one singular engineer that you need.
Yeah, no, you are absolutely right. We need people from every different discipline, not only engineering, but also non-engineering. So for instance, at the Jet Propulsion Lab, where I was a director for 16 years, we had about 7,000 employees. I call them 7,000 explorers, because what we're doing is exploring. And we have every discipline in engineering, be it electrical engineering, mechanical, aerospace, material science, every possible discipline of engineering or science. We have people in that area. We had people who are in the public outreach to explain to the public what we do. We even have artists, in there who kind of to do displays at museums about what we're doing. Computer science, business people, because in a sense, these missions typically, these missions are many hundreds of millions to billions of dollars. And therefore you need to do all the budgeting and all the planning, for it. So when students usually ask me, what should I study if I want to work in space? I tell them, just do well in whatever discipline you are in, because people need it from all variety of talent to be able to do these missions.
Thank you. Yeah, I think that's very clear, because a lot of people always ask me, what should I study if I want to do this? What should I should I get into astronomy? Can I work in this field, and so forth? And I think it's very critical from someone in your position and your experience to give them that understanding that you need to be passionate about what you do in order for you to succeed. And you can definitely participate as a team member here.
Yeah. So the bottom line is, do things that you enjoy doing, that you really are passionate about, no matter what is the discipline. And that's the best advice that I can give to people, is because you are going to be spending your life working in that field. So you want to be passionate and enjoy doing that.
Absolutely. So with that, I would like to take some questions that people wrote, and I'm going to read them to you. The first question is about the margin of error when you land a rover. What is an acceptable margin of error, and how do you mitigate that error?
That's a very good question. We can tolerate very, very, very little error, because as we are, and particularly the landing, that's where the challenge is. During those 5 minutes, we literally have hundreds of events which have to happen. Like you have the heat shield, you have to open the parachute, you have to be measuring the distance to the surface, you have to fire the retro rocket, deploy it. So effectively, everything has to work perfectly. So we really cannot even tolerate one error. And that's why we do a lot of testing, ahead of time. And we have redundancy, because we cannot joystick it. If a problem happened, by the time we find out about it, the 20 minutes of signal, it's too late at that time. So we do a lot of testing and a lot of verification ahead of time, during the lab, and there is always a risk. And usually what we do to kind of reduce our possibility of error, we test the hardware to an extreme. So for instance, if I want to measure, if I expect the temperature to be up to, let's say, 50 degrees, we will test it to 100 degrees to make sure we have margin in that area. Or sometimes we test it until it breaks, so we know where is the limit of that hardware, so we stay away from that limit. So we have developed a lot of capability of testing to really keep the error to an absolute minimum.
Now that you mentioned the latency and the 20-minute to send a signal and to receive a signal, so that's like 40 minutes total. The question is, are there pre-programmed sequences within the rover to do its job? And then how do you, when you anticipate to make those changes, you do it 20 minutes before you want the change to occur?
Yeah, Michelle, that's absolutely correct. Basically, we program everything in the lander, and we have a clock on board, and we basically, as you heard during the landing, we are regularly measuring the distance to the surface, with a radar instrument, and that's so the acceleration and the distance to the surface, that's what drive all the sequence, that we have in the spacecraft, about when to open the parachute, when to drop the heat shield, when to fire the retro rocket, and so on. So yeah, all of these are pre-planned and pre-programmed into the spacecraft, because by the time we receive the signal here on Earth that we enter the atmosphere, actually the landing has happened, because we are kind of almost anywhere between 10 to 20 minutes, behind it. So yeah, everything has to be pre-planned and pre-programmed.
I also heard that people that work closely with the rovers that get sent on Mars actually stay in labs in which their clocks are synced to Martian time. So there's a 37-minute difference. And so it's like when they come out of the lab and go home, they get like confused to Earth time. Is this correct?
Yeah, no, it is correct, because the day on Mars is 24 hours and 40 minutes. So every day you are moving 40 minutes. So if we are coming to plan, because usually we plan during the night on Mars, we develop what programs we want the rover to do. So during the day, particularly in the solar power, then it executes that. So it's like continuous jet lag. One day you come at 8 o'clock, the next day at 8:40, the next day at 9:20, and so on. So now, after a while, it became very hard for the drivers of the rover to operate. So now we plan like 4 or 5 days at a time. So we tell the rover what to do for the next 4 or 5 days. That makes it a little bit easier for the different teams who come in, and we have different shifts. But you are right, at the beginning, it was a very big challenge to stay awake.
So another question I have here says, why was Mars InSight launched from California and not in Florida, similar to the Perseverance rover? Is there like a...
No, the Perseverance was launched from Florida.
Correct, but they're asking about Mars InSight was launched from California.
Sorry. Well, we can launch from both places.
But is there a specific reason why Mars InSight rover launched from California, or no? Not necessarily.
Yeah, no, it was launched one mission we launched from California, because it depends on the trajectory that we're doing. In general, for most of our planetary mission, we launch them from Florida. But every once in a while, depending exactly the trajectory we want to send, we can actually do it also, from California to do that. Now, Earth orbiting mission, they can be launched from either place. In general, they are launched from California, or if in case of Europe, they are launched from South America.
So, and then I have another question regarding Mars and whether colonization can be anticipated by 2050, and will it be possible for humans to colonize Mars?
Yeah, the answer is yes. I mean, we do know what technology we need to be able to travel to Mars. And I think within the next 20 years, I think we'll be able to do that. Now, the big challenge is not only the technology, but as I mentioned earlier, you have to take all your food, all your water, all your medicine, and you are sitting in a capsule, for like 9 months to get there, with your colleague. There is also a psychological and physiological challenge, and you are in zero gravity during that period, or very low gravity. So that's why the space station has been very helpful to learn how do you live for a year, in space, and then going to the moon will allow us to operate in low gravity environment in preparation, to go to Mars. So if some of the audience have watched the movie The Martian, that movie is pretty realistic. I mean, there was exaggeration like every every movie you do dramatization and so on. But it's pretty realistic that in the next 20, 25 years, we'll be able to do what you saw, in that movie. Now, still, as I mentioned earlier, on Mars, you cannot just walk outside. You still have to have space suits because the pressure is very, very low. And so one of the things we are doing now is to demonstrate how can we generate water and grow things on Mars and extract oxygen from the atmosphere of Mars. These are experiments we are doing on Perseverance, which is on Mars now. So we don't have to take oxygen with us and water with us. So if we can get it from local resources, that will simplify the mission significantly.
And some people were typing in the chat about the 9-month being a difficulty. The 9-month is mainly as a result of the technology we're using, which is a chemical rocket. Now, if we were to use a nuclear thermal propulsion, that technically will enable you to get there in 3 to 4 months, assuming the technology can be finally invested in. I know NASA has been working on it significantly in the past and is continuing to do so now.
Yeah, you are correct. And I know you have been working on some of the nuclear technology. Yeah, if we can develop nuclear propulsion, which is possible. There is research going on now to be able to do that. Yeah, we might be able to get the trip to be more like 3 months instead of 9 months. And that will make a huge difference. So yes, come 20, 30 years from now, we might be able to do that in much shorter time. And that will make it much easier for traveling to Mars. It still will be a challenge, but it will be much easier than now. Somebody I see on the chat asked, what is the movie? It's called The Martian. It was a movie which was done about 2 years ago. Jessica Chastain was the astronaut on it.
Yeah, I think I typed it just in case that they missed it. So another question there's 2 questions related to the Mars aspect. One is exposure to high radiation and how we can protect astronauts from that cosmic radiation, whether on the surface of Mars or as they travel through space. What are ways to mitigate the exposure?
Yeah, I mean, when we are going in space, we put shielding. So you can shield the spacecraft from the radiation. Once you land on Mars, the atmosphere shields you a little bit, not completely, but it shields you, so it helps. So yeah, we have to have habitat that the astronaut will be living in, and then the spacesuit has to be designed properly to protect from the radiation, similar to what we have on the space station. There is a lot of radiation where the space station is, and it's shielded, from it.
What materials are used? I know water can be used as a shield, but what other materials? I mean, water is pretty heavy, so
you use different kind of material will shield you from radiation. So there is a whole variety of combination of material that can shield you, depending how intense the radiation. And as I said, fortunately, around Mars, it's not too bad. It's not like Jupiter. Jupiter is really bad radiation. So around Mars, it's a solvable problem. We have the technology to do that.
Sounds good. The other question I have related to Mars, someone is asking, is the ice on Mars, does it have other elements mixed in the ice? And how do you try it, like iron or some form of carbon in there that you could extract out?
Yeah, no, I think the ice is mostly made of water and carbon dioxide ice, because of the atmosphere to do that. But it has plenty of water, because when we landed, we had one mission which landed at the North Pole, of Mars, and we actually did scratch the surface and we did see the ice, which is just below the surface. So we believe in many areas around Mars, just below the surface, you actually have frozen ice meaning H2O, ice. So we are pretty confident that we'll be able to extract water. The question is to find where it is and how deep below the surface. So we want to be at a place where it's not very deep, so we don't have to drill too far. But at the polar region, we know that the ice cap is made of water ice.
Thank you so much. And I think we only have 20 seconds left. So with that, I want to thank you so much for your time and for your effort. and for coming online such an early time in California. We really appreciate it. And I hope everyone learned something today and is excited about joining fields related to space. Thank you so much.
And I have to say, you know, the Kingdom is playing now an important role in getting engaged in space exploration. So I look forward for the Kingdom to play a major role, both in Earth observation as well as in planetary mission. And have a good evening, everybody.
مع السلامة جميعا. شكرا لحضوركم ونتمنى لكم يوم ممتاز. شكرا جميعا.